My name is Yogesh Singh. I'm from ISER Mohali. I'll be the chair for this morning's session, which includes 3 talks of 1 hour each. And the speaker has 60 minutes, including 10 minutes for discussions. So the first speaker is Joel Moore from UC Berkeley, and he will be talking about dynamical effects from topology in metals.
Thank you. I'm a repeat customer of these ICTS meetings, and you can tell I find them worthwhile. I'm especially honored to be at one where Senthil is the guest of honor. I first met him when I was a visiting graduate student at KITP, and it became clear that there was this very unusual postdoc who was very knowledgeable and was also very generous with sharing his knowledge. In fact, almost wherever I sat in the KITP building, I could hear him sharing his knowledge. But I learned a lot from him over the years. I've continued to learn stuff since then, so it's great that he's this year's awardee. So I want to talk about something that's a continuation, if you like, of one topic he's covering. He's talking a little bit about topological insulating phases and SPT phases and so on. I'm mostly going to focus on metals, gapless systems here, where things that are topological or geometric often give you a special response. It may not be quantized, but it is controlled by some interesting geometry, basically of gauge fields inside the Brillouin zone. In fact, a lot of standard gauge field objects from high energy physics turn out to mean something in condensed matter. That first became clear with the quantum Hall effect around 1980, but there are more and more examples, and I started this talk with some stuff about the cuprates. We don't really understand anything new about the cuprates, but there's an experiment from 1935 that it turns out we now understand in quartz. Quartz may not be the most exciting material, but at least it's something. So the general theme is geometry of electrons in, let's say, perfect crystals. And I want to give one way of looking at topological phases, but I'm going to focus on many important non-quantized property of solids that have a geometric origin. And in particular, things that I can understand with a fairly simple calculation based on Berry phases in the Boltzmann equation. So one reason why I kind of like talking about this is that a lot of the calculations are basically pencil and paper, and I can go through them quickly without having to resort to some very complicated field theory or something. We got interested in a particular problem that is my main story because of some classic experiments of Kapitulnik, Aaron Kapitulnik's group at Stanford, on the cuprates, which are measuring optical rotation. If you bounce light off a cuprate, it appears that the plane of polarization has rotated, which is either a sign of time reversal breaking, magnetism, or chirality. And which one of those it is has been a somewhat active controversy over the last few years, and I'll give my opinion later. And I should say, for this first part of the talk, my main resource has been my experimental colleague, Joe Orenstein, not just for experimental suggestions, but for theory as well. So that's been a pleasure. We have kind of a long-standing 5-year collaboration in this project of trying to understand everything in solids that is controlled by Berry phases, by the geometry of wave functions. And then second, to connect to real topological order and Majorana fermions and things like that, I have a part at the end, which is some recent work on quenching and how Majorana fermions give you a unique signature in quenches. It's okay if I don't get to that, so please feel free to interrupt. I'm fine if I only make it through part 1. So one of the recent bits of progress in the cuprates is that there does seem to be some kind of order in the pseudogap regime. So just as a quick reminder, there's an antiferromagnet. There's a superconducting dome that we've known about for a while. There is some strange metal behavior in transport above the superconducting dome, which may or may not have anything to do with quantum criticality. But first in X-ray measurements and then in some other measurements, it seems like there is an onset of charge order that may explain some of the complicated physics known as pseudogap physics. And what's a little bit challenging is to understand how the observation of charge order and maybe the simplest way to state what is required to explain the X-ray experiments is that C4 symmetry, like the symmetry of a square, is broken down to something like the symmetry of a rectangle. It may not be very long-range ordered, but there's definitely some tendency towards spatial symmetry breaking here. That symmetry alone is not enough to explain these Kapitulnik experiments. There has to be something else going on, but the Kapitulnik experiments onset in roughly the same range of temperature and doping. So it may be worth trying to figure out what the connection is. So this Kerr signal, that's the Kapitulnik experiment. Just to define some words, when you send light through a sample, and the polarization rotates, that's the Faraday effect. When you bounce light off a sample and it rotates, that's the Kerr effect. You might think they're the same, and they are almost the same in magnetic materials. It turns out that they're quite different in chiral materials, materials that you could think of as having sort of a screw nature. So, yes? Yes. I'm not sure is the quick answer. The signal is not strong there, but whether that means that there's no order, or, I mean, presumably this is a binary question, whether or not there is charge order. So I think the point is this is where they have samples. I think it's hard to make non-strongly disordered samples once you get to even lower doping, may be part of the puzzle. So as far as I know, this is just an experimental statement. You're right that if there is a standard order parameter, the transition shouldn't just be able to disappear unless it's something exotic. Okay, so these are examples of that data I mentioned from the Kapitulnik group, and the basic phenomenon is the onset of optical rotation. So the vertical axis in microradians is how much did the plane of polarization rotate in bouncing off the sample. And there is a fairly reproducible experiment in different crystals. There are some subtleties about this effect, though, that make it hard just to interpret as time reversal breaking. So time reversal breaking has a very long history in the cuprates. Kapitulnik first started working on this around 1990 to rule out anyon superconductivity. Then they built a better instrument, and now they do see some signs of time reversal breaking. But the biggest challenge for a straightforward magnetic explanation is the following. Normally, to explain this, you would need, first of all, fairly large domains of the time reversal breaking. If you had smaller domains than the optical spot size, you wouldn't expect to see this. Second, if it's related to time reversal breaking, you ought to be able to train the signal in a magnetic field. It ought to be that if you cool it in one magnetic field and then you cool it in minus that magnetic field, you get opposite signs of the signal. And experimentally, that doesn't usually happen. It's hard to train the sign of the signal with the magnetic field. So that's one puzzle. And that led the Stanford group a couple of years ago to maybe reinterpret and say, okay, maybe this is not measuring time reversal symmetry breaking. Maybe this is measuring chirality, which can give you a Faraday effect. If you like, if my material is kind of rotating as I go through it, even if it's time reversal symmetric, that can rotate the plane of polarization. But there's a subtlety why I don't think that can explain this experiment. So this is the Kerr effect. As I said, I rotate the plane of polarization, and the Stanford experiment is a very sensitive interferometer that works at normal incidence. So light bounces off the sample, comes back, and in a time reversal invariant system, if there were no dissipation at all, there's kind of a quick argument that this shouldn't happen, but real samples have at least some linear attenuation. And I'm going to quote an old and fairly complicated argument of Halperin that says that if this happens, then your material has to break time reversal even if you include linear dissipation. So basically the Onsager relation, something fairly deep and macroscopic, require this to be zero, but not the Faraday effect. In other words, transmission and reflection are basically similar in magnetic materials, and they're very different in non-magnetic chiral materials. And what got us interested is in trying to understand why that happens, because we can write down a microscopic description of what the electrons are doing, and we wanted to figure out, we kind of convinced ourselves that Halperin's Onsager argument was correct. Why? You know, microscopically, what is it about the equations of motion that forces the Kerr effect to be zero? And in the process, you come across something that is related to the chiral anomaly in Weil semimetals and some other stuff. It turns out that there's sort of a topological reason why this Kerr effect is zero if I have time reversal. But I want to build up to that. I need to first of all introduce a few things about what are the equations of motion I'm going to use and what's topological about them. So maybe let me skip this slide for now. So it's still a problem that the non-zero Kerr effect in the experiment requires something that's static in time and fairly large domains because the optical spot is fairly large. I do have a guess for what's going on in the cuprates, which is a magnetoelectric effect that maybe someone can ask me about at the end, but it's not directly connected to the actual calculations I want to talk about, which I think are more interesting than my speculation. So again, those earlier experiments were YBCO. Now in another high-temperature superconductor, BISCO, there's a nice agreement between where the Kerr signal onsets and where things seem to change in the pseudogap state from photoemission and my colleague's own experiment, which is time-resolved pump probe spectroscopy. But all of these sort of measure different things. So the naive guess would be that whatever's going on is not just charge ordering. It must be something a little bit more complicated to explain the Kerr signal. So anyway, there's at least an agreement on where does this order in the pseudogap region turn on. What exactly that order is a good open question. And I'm not going to tell you the answer. I'll tell you one thing it's not because of this Kerr effect vanishing argument. And I do have a guess for what it is, but it's hard to prove it. So as I said, yeah, this seems to always coincide with the charge order in not just IBCO and VSCO, but LBCO as well. So there is actually some universality among different materials, which is nice in the cuprates. So here is maybe the problem in one sentence, or why the Kerr effect is interesting. If you just wanted to explain photoemission, X-ray, et cetera, the most natural symmetry to break would just be C4 down to C2. You've gone from your A and B axes in the plane being the same to being slightly different. That would lead to so-called linear birefringence, where the index of refraction along X is different from the index of refraction along Y. That's exactly what this interferometer is designed not to measure. And I think it is correctly designed. So that means there must be something else going on than just the simplest symmetry breaking, if you believe the experiment. So what's going on is basically the right circular versus left circular polarization. I would like to understand how the reflection coefficients of those change, but I want to focus here more on the microscopics than what's actually measured. So I want to think about the electrons in my sample and try to figure out what is it that underlies in a metal, is what I'm going to focus on. And it's going to be a pretty simple metal except for the Berry phase. The difference in reflection coefficients between left and right circular polarized light. So this is essentially a difference between n plus and n minus, if you like, rather than nx and ny. So as I said, or just nematicity. Nematicity is maybe the current buzzword in the cuprates. That alone cannot explain the Sagnac measurement for fairly simple reasons, unless you believe that they greatly built their experiment improperly, which I think is unlikely. So what can give this? Well, this is where people have been active in the last couple of years in trying to come up with possible explanations for that experimental data. So magnetic material has both Kerr and Faraday non-zero in general. I'm going to give a microscopic picture for why chiral T-symmetric materials, so basically materials with low spatial symmetry, and I'll draw some pictures and write down an actual Hamiltonian, those will have Faraday and not Kerr. The macroscopic reason why that's true is Onsager reciprocity, which was in a little-known paper by Halperin from around 1990 that everyone forgot about until the last year or two. So if you just have chiral stripe ordering, et cetera, it can't explain the Stanford experiment, at least in linear response. Why that's true microscopically is because of something we're calling topological tracelessness. It's related to when the chiral anomaly vanishes. So that understanding this without having to invoke Onsager, but actually doing a microscopic calculation, that's sort of story number one. And in particular, I think in all chiral materials, at least at low enough frequencies, it's the Berry phase that's the key ingredient for Faraday rotation. And let me give kind of a philosophical argument later. But basically, if you're thinking about electrons in a solid, and you're interested in an effect that is only non-zero when inversion is broken, then it has to come from the wave functions. It can't just come from the band structure, because E of k is equal to E of minus k, even if I break inversion, as long as I have time reversal. So if you like, just using a Gellium model or even Gellium plus interesting band structure is not going to give you any effect like Faraday rotation in chiral materials. You need the wave functions, and at low energy, the simplest thing that comes out of the wave functions is the Berry phase. And yeah, how this happens microscopically is this topological tracelessness. So I'll come back to that. And now I need to define what is a Berry phase, what is the general scheme of interesting stuff that happens because of wave functions. So I think you all know, I think I might have presented this slide at a school here a couple of years ago. If I look at electrons in a crystal, there's a part which is a plane wave, just like a free electron, and then there's a part which is periodic with the periodicity of the Brillouin zone. So if you like, electrons get a nice additional structure in a solid. Normally we forget about this. We just think about E versus K, Or if we think about this, it's just for things like matrix elements and optical transitions. But there's more to the story. You can use these to define gauge fields, either abelian or non-abelian. And every natural object that you make out of the gauge fields that come from the periodic part of the block state seems to mean something physically. We have a lot of examples of that now. So I think that's surprising. So just as background, this K, so-called crystal momentum, you can think of this as living on a d-dimensional torus. Basically, the Brillouin zone has periodic boundary conditions because it's a crystal. So let me now justify this idea of Berry phases, that something from the quantum mechanics of U sub K is going to give me a field strength, which geometrically you could think of like a curvature. So the Berry phase idea is that the adiabatic theorem we all learn as undergrads is only part of the story. The adiabatic theorem is that if I have a non-degenerate state of a quantum system and I smoothly change the Hamiltonian, then I don't have any transitions out of that state. But the rest of the story is that if I go around a closed path in parameter space, by the time I get back to where I started, I may have picked up a phase, and that phase is actually observable. And I'm going to write that phase like a vector potential in parameter space. For us, the parameter is just going to be crystal momentum. And why do I write it as a vector potential, and how can I convince you that this is physical? Well, the reason for writing it as a vector potential is that it has exactly the same gauge invariance as the vector potential in E and M. So everything you know from E and M, you can kind of take over and apply here. So what I mean by that is, so I had to define this vector potential by using a reference wave function in momentum space. At every k point, I chose my definition of what the wave function for this state is. And since we're now talking about a non-degenerate single state, the only way that you and I can differ is by a phase. Let's say that I chose psi sub k, and you chose some different phase convention. Let me just assume that it's smooth. Then if we make that change, then A changes by the gradient of our phase, just like in E and M. And that's a clue that if we want to make gauge invariant objects, physical objects shouldn't care about how you and I defined our phases. They should be things like curl of A, for example. We all know that curl of A, we lose the gradient. The way that non-abelian fields arise is there are a lot of situations in solids where either multiple bands are degenerate. In other words, I don't have a one-dimensional degenerate subspace. I have an n-dimensional degenerate subspace. Or even if they're not degenerate, it could be that maybe I've got n-occupied bands. Energy differences between occupied bands usually don't matter very much if I'm not making transitions. So what that gives me is a non-abelian connection where alpha and beta are band indices. And it turns out that if you want to write a compact expression for 3D topological insulators and the magnetoelectric effect and stuff like that, that all depends on the non-abelian part of the Berry connection. As far as I know, that's the only thing. The magnetoelectric effect is the only thing we know so far that depends on the non-abelian part. Everything else depends on abelian stuff. So I'm going to mostly talk about abelian stuff. But if you want an open problem to think about, there are probably other physical consequences of this non-abelian thing that we just don't know yet. So the first physical property coming from this kind of Berry phase in a solid to be understood was the integer quantum Hall effect. So Thaulis et al. Were thinking about, OK, suppose I take a two-dimensional crystal in a magnetic field. And let's say that the magnetic field is such that I can still define block states, which basically means that the magnetic field's flux per unit cell is a rational multiple of the flux quantum. If that's true, then I've got block states, and there ought to be something about the block states that tells me I have an integer quantum Hall effect. So what is it? And the answer is it's this Berry curvature. More precisely, it's what we think of as the field strength in E and M. If I integrate this over an occupied band, that is over the Brillouin zone, which is now a two-dimensional torus, in the right normalization, I get an integer. So this combination of the u's, this is just writing out what f is. So if I integrate f over a band, I get an integer. That integer is a topological invariant, and that integer, sometimes called Chern number, is just how much does that band contribute to the integer quantum Hall effect if it's completely filled. In other words, I add up these Chern numbers for all the filled bands, and that gives me the n that appears in sigma xy equal to ne squared over h. So that's the first example. The Berry curvature is something physical. Now, this is my quick list, since this is one talk, not a lecture course, I cannot say all the things that depend on Berry phases, but here are the ones we know. And as I said, this kind of kicked off around 1980, or I guess 1982, with that Dowless et al. Picture of Chern numbers and the quantum Hall effect. So one class of topological, and this is all basically non-interacting physics, one disclaimer. So topological phases where I don't care about symmetry, things like the integer quantum Hall effect, that doesn't require any symmetry to stabilize it. Of course, I need to break time reversal symmetry to get into it, but it's not symmetry protected. That has topological expressions in both 2D and 4D. The simplest class maybe of symmetry protected topological phases are topological insulators, which are non-interacting fermion topological phases. In 2 dimensions and 3 dimensions, there are similar topological invariants, which you can write as integrals over the non-abelian Berry phase. So for example, in 3D, this is simplest. If I form the Chern-Simons form of the non-abelian Berry connection in a solid, that tells me its magnetoelectric effect. And if I have time reversal, that quantizes it to Z2, in other words, one of 2 possibilities, which are the ordinary insulators and the topological insulators. But, so those are the topological phases. There are plenty of other things that depend on Berry phase, and maybe the classic one, the realization that there are new things even in old problems. Electric polarization seems like about the most old, boring thing you can imagine in a solid. It's just, where does charge sit? If you try to calculate electric polarization just by taking one unit cell and looking at where charge sits, the problem you'll run into, you can convince yourself by doodling on your paper, is that it depends on where you draw the unit cell, what the polarization is. And that's kind of a clue that something more interesting is going on. It turns out that if you want to calculate electric polarization in an insulator from a unit cell, you need to use the Berry phase. It's basically a loop integral of A over the Brillouin zone. The magnetoelectric effect, that's something we worked on for a long time. That is connected to the 3D Z2 topological insulator. That's an integral over non-abelian Berry phases. And the subject of this talk is mostly metals. So I'm going to talk about 3 effects in metals that I think are controlled by Berry phases, at least in part, maybe in all, and then lead into this new one, which is the optical gyrotropy, the rotation of the plane of polarization. So polarization, just to understand how that works, if I have a one-dimensional system, to make it simple, polarization is charge times the sum over occupied bands of this object, where the U's, again, are my periodic part of the block state. And if you want a very rough intuitive idea, this is just A, that Berry vector potential. If you want an idea of why this appears, well, if you had a plane wave, taking the k derivative would give you r. So something about the A, the vector potential, tells you where does the electron sit in the unit cell. And that story is going to be crucial when I talk about metals. So if you want the simplest physical interpretation for what the abelian Berry phase is describing, it's describing something about the physical location of electrons in the unit cell. Now, polarization is not quantized in general unless I add some symmetry. It's just a simple physical observable, but it is completely controlled by the Berry phase. That is, the electronic contribution to polarization is just this integral. In higher dimensions, it's still just this integral. So if you want a reason why, in hindsight, it kind of had to be a Berry phase, this is that philosophy I gave you before. Anything related to inversion breaking in a time reversal invariant system has to depend on the Berry phase at low energy, because it can't just, because the band structure is not sensitive to the fact that inversion was broken.
I think that any properties of transport can be expressed also in terms of.
Yeah, I think I'm.
Maximum properties. I have done some.
I see. Well, I'm going to talk about, yeah, I'm going to talk about the anomalous Hall effect in a moment, which is a transport property. Yeah, so yeah, this is just what I mentioned about, this is my advertisement that if you want something that is not well understood and you have a field theory background, then non-abelian Berry phases in solids, we know the magnetoelectric effect is one example. We don't know others, but that doesn't mean there aren't others. So now.
Would you mind saying in a sentence what the magnetoelectric?
Yes, it's so I'm glad you asked. Can I take more than one sentence? So if I form this combination, dp by dB, where P is electric polarization, B is magnetic field, or alternately dm by dE, that is the magnetoelectric effect. I'm specifically interested in the electronic contribution to this. Now, the way this connects to something that you know better than I do is if I ask what kind of terms would give me this, and specifically, the interesting part is the diagonal part in spatial indices. Well, that would be associated to a term in the Lagrangian, which is something like E dot B, so-called axion electrodynamics. At least that's what condensed matter people called it, so a theta term for the electromagnetic field. And that means that a compact derivation, basically people like Wilczek and Sakivi and maybe others, knew the effective theory of topological insulators before there were topological insulators. Topological insulators we think of as theta equal to pi in the right units, and ordinary insulators are theta equal to 0. So in a sentence, this is the abelian electromagnetic field that I actually measure. But theta, not just when it's quantized, but in any material, there's a contribution to theta, which is an integral over the Brillouin zone of the non-abelian Berry gauge field. So there are two gauge fields in a solid. There's ordinary abelian electrodynamics, and then there's this Berry stuff in the Brillouin zone. The Berry stuff, the non-abelian aspect of the Berry phase is what controls theta. So that's the magnetoelectric effect. So maybe another way to state it, a more mathematical way to state it would be the Chern-Simons form is a nice object because it's almost gauge invariant. If I take the Chern-Simons form as a 3D integral, large gauge transformation will shift it by 2 pi times an integer or something, but that's OK. We kind of know what that means. If there are any other objects you could think to make out of this non-abelian gauge field, they might be physical. We could try to figure out from symmetry and so on what could it be that they control. So I told you before, so this is, I think, the biggest mistake most of us now believe in Ashcroft and Mermin. Ashcroft and Mermin is an incredible book. It's still the standard book. You know, it was written in 1977. But there's something that Karplus and Luttinger had actually worked out even before then, but they didn't know how to express it in a very compact way, and it was very controversial, so it wasn't included. So this is the equation of motion for a wave packet in a solid, the position part. So maybe a way to argue why something might go on is that if you look in Ashcroft and Mermin, there won't be this term, which means that the equations are kind of not symmetric. They're not nicely symmetric or dual between position and momentum, because the momentum equation has E plus V cross B, basically. In other words, it's got electric and magnetic fields. There are two terms in the momentum equation, but in the position equation, there's only one. So we now think there's a second term there, where that F is the Berry phase, and here's why. The way to think about this second term, F is dA by dk. So this is dA by dk, dk by dt, something like how is A changing in time because the electron is moving through k space. The way to think about what that term describes, the first term, the group velocity, that would be there even if electrons were point particles. It doesn't care at all about what the electron is doing in the unit cell. Suppose the unit cell has two different atoms, A and B, and maybe A is on the left and B is on the right or something. As k changes, maybe the wave function moves from being concentrated on A to being concentrated on B. Then there's kind of an internal velocity or anomalous velocity within the unit cell. That anomalous velocity is what this term describes. So there are various derivations of it. I think everyone agrees this term is there. Getting from this to physical consequences is sort of the hard part. But there are three effects in metals, at least three, that I think are sensitive to the existence of this term. So the oldest is going back to Hall. Hall, the same Hall effect person back in the 19th century, realized that if you take a magnetic material like iron, you don't need to apply a magnetic field to get it to have a sigma xy, a Hall effect. It has it just in its own time reversal breaking. And at least part of that comes from this term. In other words, it doesn't just come from the magnetic field, it comes from the time reversal breaking in the band structure. Second, helicity-dependent photocurrents are something I worked on with Orenstein a few years ago. That's saying that if you take some two-dimensional quantum wells, say, with fairly low symmetry, but not 3D, just 2D, then you often have photocurrents where, say, right circular light gives you a photocurrent one way, left circular light gives you a photocurrent the other way. That's been measured for at least 20 years or so, and we think it's a Berry phase effect, and I would like to think we've convinced people. And then the subject for today is this three-dimensional chiral materials. The way optical rotation happens has something to do with the Berry phases. So the anomalous Hall effect is a very old and still difficult problem. There's a quite comprehensive review article. I'm not going to try to cite all the work on it, but if you want to learn more about it, this Naga-Osa et al. From Museum of Modern Physics is there. But basically, the interesting part of the story, you can tell it's still an open field because the punchline figure at the end of like a 50-page RMP is a speculative and schematic phase diagram, which is kind of depressing after 100 years or so of study. But basically, the idea is that there is a region where the same quantity, the integral of the Berry curvature that would be quantized in the quantum Hall effect, gives me a so-called intrinsic contribution to sigma xy. Intrinsic in the sense that it doesn't care about scattering details and so on. It's just a property of the band structure of occupied bands. If you want, you can rewrite this as a more complicated Fermi surface expression. The reason why this is a hard problem maybe is that this term is believed to dominate when the sample is not too clean or too dirty. It's kind of an intermediate coupling phenomenon, which we all know are the messy problems. So the two other effects, the circular photogalvanic effect, let me give you a quick picture of why that happens in metals. So this is an example of experimental data showing that the photocurrent that you measure along one direction oscillates with the sense of circular polarization. And here's an example for why circular polarization gives you something. If I have low frequency circular polarization on a metal, so first of all, if I had a constant electric field on a metal, the effect of that, let me get out of the way. If the solid line is the ground state electron distribution, then the electric field just kind of pushes the electrons over a bit, and then it reaches a steady state. If I've got circular polarized light, this dotted circle kind of rotates around. And in that process of rotating around, over a period, the ordinary velocity cancels. But the anomalous velocity doesn't, because when it's displaced a little bit this way, the Berry curvature is pointing one way, and dk dt is pointing down, let's say. When it's displaced over here, both of those have flipped sign. So overall, I get the same sign. So essentially, the anomalous velocity doesn't average to 0, while the anomalous velocity does. And we do think that this big set of experiments, mostly in Regensburg by a group led by Ganichev, are pretty strong evidence. They basically thought it was due to spin-orbit coupling. They saw it in gallium arsenide for many years. Then they tried silicon, which should have much weaker spin-orbit coupling. And they saw essentially the same strength of effect, which was a clue that it has nothing to do with spin-orbit coupling. And now I hope we've convinced them it is a Berry phase. So the story for today is chiral materials, which are now, this is only a three-dimensional effect, so the pictures have to be a little bit more complicated. We started working on this around 2012, and then we realized it's more interesting than we thought just in the last year. So here is what has to be going on microscopically to explain why Bert Halperin is right that the Kerr effect should be 0 with time reversal. So I want to write just kind of general expressions for how my current depends on the electric field. So normally, the bulk gyrotropic effect in a chiral material is of the form some proportionality constant, something material dependent called gamma times dE by dz. If the material is changing, you might form two simple guesses for how this equation should work. Your simplest guess might be that I get sort of a total derivative property where I get d gamma by dz, or I just don't have an additional spatial varying term. The correct answer has to be that there's a factor of 1/2 here. So one reason why we didn't think this was that interesting until recently was that you're basically trying to explain a factor of 1/2 that you sort of know has to be there. It turns out that the way the factor of the half comes out explains a whole bunch of other things. But this is where we started. So I'm kind of trying to take you through our honest thought process rather than present things in what would have been, in hindsight, a more logical way to figure it out. So we were curious about what microscopically is going on to explain this factor of 1/2. So I don't think until recently it was clear why this had to be there. It just had to be there from Onsager. So here's a quick statement of the connection between Berry curvature and symmetry. If I have both inversion and time reversal, then the Berry curvature is 0. If I break time reversal, then the Berry curvature can be non-zero even at the origin. It can average to 0 over the ground state, and that's the anomalous Hall effect. The case I'm interested in now is, and in the circular photogalvanic effect, is have time reversal symmetry, break inversion. Then you have an omega that vanishes at the origin. It's kind of odd in K. So the momentum space average is 0. So just in 2D, breaking inversion is not enough to give things like the Kerr effect. You kind of have to go to 3D. And we had worked out an argument for what kind of material should do this. So let me draw some pictures and then give the microscopic. So if you want a chirality, maybe the simplest way to do this, and I should say that around 2012, we were working on this, and the Stanford theorists were working on it independently, and Joe Ornstein is knowledgeable enough experimentally that he managed to get on both papers, even though we were sort of competing, so that's good. The point of this is that the material, say, it's not just enough to have ordinary stripes. Ordinary stripes don't have a direction, they just have an axis. What I would need to really explain the Kapitulnik experiment, say, in terms of optical rotation, is something like a material with a vector in a plane, and that vector rotates as I move through the material. So a fairly low symmetry structure, but this was what was hoped might explain everything in one compact story that I have, and you know, there was a little bit of neutron evidence for something like this from Tranquata. It wasn't a crazy idea that this might be what's going on in the cuprates. So there's kind of a handedness of the material. If I have material that does this, how do I couple it to light and get the Faraday effect, say? So if you go to momentum space and ask what's going on, the neat thing that happens is if I look at a plane up here, basically at fixed kz, this plane of occupied electrons can have a non-zero average Berry curvature. At equilibrium, it will cancel out the Berry curvature average down there, but when I put on light, even at linear response, I can basically have a different occupancy up here than down there. There's a non-zero average, and something interesting thing happens. And I'm not going to go, and this is what I was saying, that sigma xy for this plane is the integral of the Berry curvature over that plane, so it could be positive here, 0 there, negative there. They cancel in simple measurements, but not in this optical rotation. And what I sort of want to focus on, let me not give the hand-waving argument. Let's say you trust me to solve the Boltzmann equation and so on. Let me focus on what's kind of topological or interesting, the quantity that appears in the calculation. So this is a result that we derived in the earlier paper. To test it, we kind of wrote down a tight binding model that had exactly the symmetries of this picture. And what you find is that optical gyrotropy for light in the z direction, so how much does it rotate, is proportional to a somewhat strange combination. And the new work is basically realizing that there's a lot of interesting stuff about this combination. But basically the combination is, if you want to know how strong is optical rotation in a chiral material, it's an integral over the occupied states of the Berry curvature in the z direction times the group velocity in the z direction. So something that mixes energetic and topological or geometric aspects. So you might think that this is some messy combination that couldn't have anything nice about it. That's probably what we thought if you'd asked us, but there is something interesting about that combination, which other people had thought about a little bit in a different context, this chiral anomaly. So the new calculation was to try to understand this 1/2, and in doing that, you work through the details and you get, at first glance, you don't get the 1/2. You just get an additional term. But you realize something weird goes on. When you do the calculation for spatially varying chiral order, you get the term that you have in bulk. And then you don't get a 1/2. You get the same thing back, except it's x instead of z. So in other words, the only way for that 1/2 to appear is if there's some magic relationship between what's going on in the x direction and what's going on in the z direction. And it turns out that there is sort of a magic relationship of that type, which is that the tensor that I make from omega sub I v sub j, if I integrate that tensor up to a constant energy, it's always traceless. And let me try to convince you why that's true. So I'm going to be interested in Berry curvature dot group velocity. So add up x, y, and z. If I do that, well, the special thing about group velocity, the only special thing about that is that it's a gradient. And the only special thing about the Berry curvature is that it's a curl. It's a curl of A. So if I do this and just do some simple vector analysis, I get the Fermi energy times the integral over the Fermi surface of the outward directed Chern number, which is 0. To be precise, it's 0 if I take the whole Fermi surface. You might know that if I took one Weil point, I would get an integer, say plus or minus 1 for this integral. But Weil points kind of come in pairs. There is a subtlety. They might be pairs at different energy, so let me come back to that. But basically, we believe that under all circumstances, this is 0. So in other words, the sum of the Faraday optical conductivities in 3 orthogonal directions should be 0. which is kind of bizarre, and we were thinking about is there an experiment that could test that. So let me come back to that story. There's kind of a sum rule. So to summarize, we said that, first of all, the bulk gyrotropy is, say, omega I v sub I. Second, everything will hang together, and I will get the 1/2 if there's a relationship between the x direction and the z direction. And it turns out that this relationship is exactly what you need. So this is enough not just to guarantee the 1/2, but more interestingly, to give you this prediction about optical conductivities in orthogonal directions of crystals. So I'll come back to that, but let me explain what this all has to do with the Weyl anomaly, which is really a hot topic, sorry, the chiral anomaly, which is a hot topic in condensed matter at the moment. So forget about optical response. I didn't want to solve the equations for you there because it'd be kind of boring, but I can do the equations explicitly for a constant magnetic field. And this is, simple problem. Take a constant magnetic field and apply it to a solid. Do I get a current? So it's kind of trivial to see from solving the Boltzmann equation, if you want to do it in detail, there's no current along x and y. But if you calculate naively, you will get a current along z if you don't realize that tracelessness property. Because basically, there's one term which is omega x vx plus omega y vy. And then there's another term which is omega z vz. Because these add together to 0, you do get 0. In fact, this idea that there could be a current along the direction of a magnetic field, that's this chiral magnetic effect, or related to the chiral anomaly, it was sort of known since people started revisiting Weyl points and so on. I mean, it goes back a long time that if you have one Weyl point, then there is a current along magnetic field, because then this trace is not 0. A quite subtle thing, people were very interested in the possibility of getting that effect in real Weyl materials, solids, if you could maybe lower the symmetry and have the different Weyl points at different energies so that they didn't obviously cancel in pairs. It turns out that even that is not good enough. This was a controversy for a couple of years. Basically, let me skip this, I think I've said. The vanishing of the chiral anomaly is that because this is 0, however much you lower the symmetry in a solid, I'm convinced, based on work of other people, that you will never get this current along B effect at equilibrium. If you perturbed away from equilibrium, sure. At equilibrium, there were some nice numerics by Vazov and friends, and then New et al. Doing the same kind of thing we did. This was the paper we found when we thought we were the first to understand this tracelessness thing. It's kind of neat that even if the Weyl points are at different energies, you would think naively that they don't cancel. But if you do the full integration over the Brillouin zone properly, they still do cancel, basically because the change in energy of this tensor is the sum of the Chern indices of all the Weyl points at all energies, which has to be 0 by sort of Nilsson eunomia. So that's saying this is a rare example. Normally in condensed matter, if you've got a Dirac point or a Weyl point, you could linearize near it and get away just with that and not worry about some bizarre cancellation from the rest. This is a case where you get a bizarre cancellation from the rest, at least sometimes. So finally, what got us a little excited was this prediction that optical rotation in time reversal symmetric materials, if I sum up along 3 different angles, we should get 0, at least at low enough frequencies. So there's a review article on this optical rotation by these folks, Yarpagnon and Shemla. And it turns out that there are cases where this happens, this vanishing happens, and it's not because of symmetry, it's because of topology. So there are 2 cases where this optical conductivity, 2 standard patterns for it along the 3 axes. One is 1, -1, 0, and that turns out usually result from symmetry. But alpha quartz, not nearly as exotic a material as the cuprates, but a common optical material where this was first measured in 1935, has the following pattern of optical rotations. It's 1, -1/2, -1/2. In other words, along Z, it is twice as large and opposite sign as along X or Y, which is actually the same structure as in that stripe model I wrote down earlier. But the point is, there's nothing about the symmetry material that really forces these to add to 0. It does force these 2 to be the same and this one to be different, maybe. But this tracelessness, we think, is really a direct measurement of the same topological property that is the vanishing of the chiral anomaly and so on. So something about this being 0, we think, is already measured, which is good because then we don't have to do a new experiment. So there's something about optical activity of crystals that we think is related to topology of Bloch electrons. So I think we can add it, I hope we can add it to the list of effects in this class, where whatever natural object you can make, and somehow this turns out to be a natural object, from electrons in the Brillouin zone will mean something physical. So just to summarize this main part of the talk, the Berry phase, we think, is at least part, and maybe at low frequency all, of the optical activity of metals. If I solve an inhomogeneous case, then I can get the 1/2 from this tracelessness property, which was already known to be interesting because it explains why there's a chiral anomaly with one Weil point and no chiral anomaly in a real material. And then maybe the big story is that this mechanism is kind of testable. It makes a non-trivial prediction beyond just what you'd expect from symmetry. And at least in alpha quartz, that material, that seems to be satisfied. So I think maybe what I'd like to do for 5 minutes is advertise a bit this work on quenching Majoranas, just because the last time I was here, Majoranas were the whole story. Everyone was very excited about them. So now that I finally did something on them, I want to talk about it. But I'll just summarize the story. So very briefly, if you haven't heard, Majoranas are fermions that are equal to their antiparticle. The electron is not a Majorana fermion because the positron is different from the electron, but the neutrino is a nice example of a particle that might be its own antiparticle. In other words, this bar that you've been forced to write if you ever took a class on nuclear physics maybe doesn't even need to be there. So there are nice experimental tests in high energy, but the story is still not clear for real neutrinos. Condensed matter Majoranas are a very fundamental thing. I would almost argue they're deeper and more fundamental than Majoranas in particle physics. They're not associated with just fermionic statistics. They're associated with non-abelian statistics. And a huge effort in condensed matter has been to try to find experimental proof that there are emergent excitations that behave like Majorana fermions. If you like, a simple way to argue that this is a remarkable thing we should try to understand is that when you take quantum mechanics, you would think that a two-level system is kind of the atom, the indivisible object. What could be simpler in quantum mechanics than a two-level system? Well, Majorana fermions are a way to take one spinless fermion, complex fermion, which is a two-level system, and break it up into two parts. Of course, you could always do this mathematically, but the question is, are there physical systems where we can tell that the electron has broken up into two pieces, maybe at different spatial locations? So the thing that we did was to try to approach this through some of the non-equilibrium physics that you heard about in Krishnendu's talk, namely a quantum quench. So quantum quenches in condensed matter, it's fashionable to talk about them in atomic physics, but there is one old example of quantum quenches in condensed matter, which is optical absorption. When a photon comes in and bounces an electron out of a core level, that is a sudden change, a quench in the potential for all the other electrons. So the Anderson orthogonality catastrophe and stuff like that, that is all really a quantum quench in modern language. So it turns out that if you do a quantum quench in a simple Majorana system, then the Low-Schmidt echo, which appeared in Krishnendu's talk, it's the how does the overlap of the wave function at time t after the quench and the wave function right before the quench, how does that fall off in time? The Low-Schmidt echo has a unique exponent that tells you that you had Majorana fermions in your system. So to kind of draw the system we're talking about, let me skip some of the experimental background for why this is plausible. The magic number is going to be 1/4. We basically want to connect an ordinary wire to a 1D Kitaev model with Majorana fermions and then suddenly disconnect them, say by absorbing a photon. And if you can do that, which is admittedly a hard experiment, then if you don't have Majoranas in the system, alpha will be nearly 0. And if you do have Majoranas in the system, alpha will be nearly 1/4. If you had parafermions, you can get 1/2, et cetera. So you can diagnose what kind of fractional particles do I have in the system by the exponent that appears in the Low-Schmidt echo after a quench. And just to wrap up my little summary, this is the picture for what's going on. So I had normal liquid, one-dimensional liquid, and topological superconductor. And that 1/4, the reason why we're excited about it is that it doesn't care about Luttinger liquid corrections and things like that. It seems very robust, and you can get it from a simple picture of what boundary condition does the coupling to the Majorana induce on the normal liquid wire. So a little bit of boundary conformal field theory, but quite simple. It comes down to boundary conditions on the 2D Ising model, if you like this kind of thing. Maybe more convincing are the numerics. If we have a Majorana fermion in the system, this Low-Schmidt echo, the overlap, falls off as t to the -1/4, and if we don't, it barely falls off at all. So this is our favorite smoking gun. It would not tell you anything about non-abelian statistics directly, so it's not as good as interferometry, but we think it's better than a zero bias peak because there are 1,000 other things that could be a zero bias peak. If you saw a quarter, I don't think there are 1,000 other things that could let you see a quarter. And to be precise, you would measure this in optical absorption. So that's kind of what I wanted to say. And I did try to leave a few minutes for questions. One question that I got, I've only given this talk once before, and one question that I got was immediately, so what is going on in the cuprates? Because you may understand what's going on in quartz. No one cares. So what's going on in cuprates, where a lot of people care? There are 100,000 papers on the cuprates. It's been a while since I saw a paper on quartz, even alpha quartz. So with cuprates, it's very hard to explain the large size of domains and the failure to train in a magnetic field. But there is an idea, which is not my idea. It's people like Varma and Ornstein and so on, that maybe you could take the Kerr effect as possibly indicating, which is maybe the charge ordering is associated with something like a magnetoelectric effect. If you have a bulk magnetoelectric effect of this type, then in bulk you will not measure a magnetic moment. In other words, you have a linear response to magnetic fields and a linear response to electric fields. But if you don't apply any fields, if you just measure the moment is 0. There are plenty of materials like this. CR203 is a simple example. But when I put a boundary on a material like that, the symmetries of a boundary in a material are like, it's as if I had a normal electric field. You could think of the boundary as like a change in the electric potential that's keeping my electrons from running away through the work function. So if I have a magnetoelectric bulk and a boundary, then I get a surface magnetic layer. And that surface magnetic layer doesn't really train because the bulk theta is not really trained by a magnetic field. And if the bulk theta is long-range ordered, basically there are a lot of probes that wouldn't detect that, but this one would. So maybe there's charge order that goes along with some magnetoelectric response, but not magnetic order in the bulk. So that is my best guess. But as I said, I don't think that any of the bulk probes of Chandra Varma's order or other kinds of magnetoelectric order are 100% accepted by the community. But otherwise, it's hard for me to figure out what could be going on in this Kapitulnik experiment other than that. In other words, I think it has to be measuring surface ferromagnetism, but it has to be surface ferromagnetism that isn't trainable. So that's my own guess. Anyway, I think I better stop there. So thank you.
Thank you for finishing on time. There have been some questions, but there's time for a few more.
So regarding the last speculation, so and another question. So to get theta due to charge order, that's charge order at least has to break inversion symmetry.
That's right. So, you have to break both inversion and time reversal in the bulk. But it's possible you can break time reversal without having a magnetic moment, like an antiferromagnet would be a simple example. But yes, I agree. The bulk has to be very low symmetry. Yeah. So yeah, and you're right. It could not be just C4 to C2. It has to develop a vector. Yeah.
Well, it can do it with just breaking inversion. But then it will have
odd
pi,
indeed,
right? Then it would have to have pi, but right. Okay.
That's right. Yeah.
Right. Yeah. Okay. And the other question is this factor of half. If I understood right, it came from in Halperin's paper and from just symmetry considerations, basically just.
And it comes actually from, so it's a little bit more than kind of conventional group theory. You need to put in like Onsager symmetries,
yes,
reciprocity. Yeah.
That's right. But then you say how it comes out microscopically from the Boltzmann equation is through a topological effect. And that's a bit weird. Or
no, I guess I'd put it this way. I mean, I think it will be true in any microscopics, because it is true. It's a general argument. But if I write down a model like the Berry-Boltzmann equation, I say, OK, I think this is a decent description of a metal, then the metal ought to be able to produce the 1/2. So it's not, I guess I don't want to claim that in all cases the 1/2 is coming from this. That's certainly not the case. But at least in this case, you do get the 1/2 if you do the calculation carefully, and you get the 1/2 because of this tracelessness. So somehow tracelessness underlies a lot of different things, which was a surprise to us.
I think you're.
Senthil, I think you missed my opening joke, but the point was that you don't really need a microphone. I think that's correct. I mean, I think that the they agree in some limited range of doping, but you would expect that the Kerr effect probably tracks what people usually call T star and keeps going up as doping goes down. And it does seem like the charge ordering is, yeah. So I think that is a fair description of the experiments, and I don't have an answer to it. Well, I guess I would tend to think that there have to be multiple orders involved. I mean, for example, it could be that, let's see, I guess you would want something where there is a nematic transition at low temperature and another transition at high temperature. And then there is a range over which the temperatures coincide, which, as you know, can happen sometimes in Ginsburg-Landau theory, that because of the interaction between ordered parameters, two fields track each other for a while and then separate, but it's not very universal. I would agree with that.
Joel, just one question regarding the second part of the talk. So in this locksmith eco, you take this system to be a closed, isolated system, and that's so that it can evolve. So in practice, is it, I mean, you know, does environment does something to this? I mean, could you see this long time till really? I mean,
I think you could see some of it. I guess the closest thing we've done to adding an environment is to add additional channels in the bulk wire, but those turn out not to couple very much and not to change this very much. I mean, I guess I would think that if there is the simplest picture would be that you have a bath, you have some relaxation time, this gets cut off. But I don't know. I guess I think that the quasi-particle poisoning lifetime, as they call it in these experiments, is long enough that you would be able to see some of this decay. I mean, I don't know, like, you might not be able to say it's precisely 1/4, but I do think that on this plot, my understanding of the experimental parameters is that it isn't a situation where the quasi-particle time is here, it's somewhere down there, but I don't know how far.
just one more thing. Have people looked at other protocols regarding this? I mean, this is just a quench, but could anything interesting happen?
Well, the problem is that if you want to have really good control over changing the parameters of an electronic system, you usually are doing electronics, which limits your time scale to the point where the electrons aren't very coherent. So if you want to suddenly change the properties of an electron system shorter than a picosecond, you more or less have to do it with photons. So I guess what I'm saying is I don't know, okay, aside from qubit situations, so if you want, you can build a very long coherence time electron system by building qubits, and then you could do quenches. In fact, one of my colleagues at Berkeley is very excited about this, Irfan Siddiqui. But if you just start thinking about electrons in an ordinary solid where you haven't tried to engineer a long coherence time, then the coherence time is a picosecond, you can't really do an electronic change on a picosecond, so you're stuck with photons, and photons are kind of a blunt instrument as far as I know. Yeah. But you could probably, I mean, it is a question. You might be able to periodically modulate the intensity of the photons. Like what we talked about is basically a one photon effect. There may be some possibility where you have a laser. The absorption time is very short, but maybe you could modulate the intensity on a time scale over which the electrons are still coherent. So I think it would have to be optical, but there might be a way to do something optical that is beyond just a simple quench, but faster than a picosecond.
If there are no more questions, let's thank the speaker once again.